All right, so moving on from our discussion about solubility rules, we're now going to apply those solubility rules to actual reactions. So what we're going to see is how reactions really occur on the molecular level, taking the molecules, breaking them, or the compounds, breaking them apart, and looking at how the ions interact with each other to give us some kind of a visible product. So we have to show how these work using our different equations. A formula equation is the equation that you're used to doing. It's the ones where you write your um, reactants and your products and you balance the equation. It's the ones that you're used to. The complete ionic equation is a little different. This shows the ions present. So this is where we're going to take a look at those solubility rules. If something is soluble in water, it dissolves in water and breaks apart into its constituent ions. Those ions then interact with each other, and depending on what happens when they interact with each other, you might end up with something called the precipitate, which we mentioned earlier, or you might end up with more ions in the solution, which appears as no reaction. Then, what we really concern ourselves with is the net ionic equation. Sometimes this is also called the total ionic equation. And what's the advantage of the total or net ionic equation is that it gives us only those ions, or those what we call species, that actually react with each other and give us a visible product. So here's an example of those. We have potassium chromate along with barium nitrate reacting to make barium chromate and potassium nitrate. So this guy here, this formula equation, is something that you're very used to seeing. Nothing new, nothing startling, nothing out of the ordinary about it. You simply write the reactants, the products, and you come up with the balanced equation from it. Then we have the complete ionic equation. The complete ionic equation then is based off of those species that end up dissolving in water. So you take a look at your solubility rules and you determine which can dissolve and which cannot dissolve. And then you have to show what they look like once they dissolve or ionize in the water. So for instance, if you look at the formula equation, you'll see that there's two potassium ions in that potassium chromate. That 2 becomes a coefficient. Why? Because this shows that there's two potassium ions that are actually forming. K won't stay together in solution as K2. It'll break apart to form two K plus ions. The chromate then, of course, forms an ion, and then we see the nitrate ions and the barium ions. But now take a look at our product. You'll notice that we have barium chromate. If you reference your solubility rules that you all need to know and memorize, when you reference those solubility rules, you'll find that chromates tend to not be soluble. And so barium chromate here sticks together as a solid. It does not form ions. But then that the potassium and the nitrate still continue to be ions for a number of different reasons. Now, when all is said and done, we really only care about those products and those reactants that actually do something in the reaction. So, very much like in algebra, we're going to take anything that's the same on either side and cancel it out. So I just crossed out two K pluses because they're both on both sides. We're going to cross out the two NO3 minuses because they're the same on both sides. And you'll end up with this net ionic equation at the end. The Ba plus 2 plus CrO4 minus 2 gives us the barium chromate. So let's practice writing some of our own. We have aqueous potassium chloride is added to aqueous silver nitrate to form a silver chloride precipitate plus aqueous potassium nitrate. Write the formula equation, the complete ionic equation, and the net ionic equation. Now that seems like a real mouthful, but it really isn't. What you need to do is break it down into its constituent parts. Look at it this way. We know we have potassium chloride, we have silver nitrate, we have silver chloride, we have potassium nitrate. We can then say that since potassium chloride is added to aqueous silver nitrate, these two must be our reactants. We know that they form silver chloride and potassium nitrate, so those are our products. Our next step then is to go ahead and write out the formulas for these and write our balanced equation. Now to keep in mind that I'm not going to slow down to show you how to write these formulas. If you still are unsure about how to write formulas, please go back and reference your notes from Unit 2, Lesson 8. That'll go through how to make formulas from the names. So if I look at potassium chloride, I get KCl. If I look at silver nitrate, I get AgNO3. They form, there's my arrow, silver chloride, AgCl, and potassium nitrate, KNO3. Now that is our formula equation. Now that formula equation is already balanced. We lucked out there. So we don't need to do any more. So we can move on to our complete ionic equation. So now we would reference our solubility rules. Potassium chloride is soluble because potassium is an alkali metal, which makes it soluble, and chlorine is a halogen, which makes it soluble. Silver nitrate is very soluble because it is a nitrate, and we know that all nitrates are soluble no matter what the circumstances. But now if we take a look at our halogen rule only holds true for all elements except for lead, silver, mercury, and a few other ones. Now if you weren't sure that AgCl sticks together and forms a precipitate, you can go back and reference your word problem where it tells you that silver chloride is the precipitate. Remember that precipitate is just a fancy word for solid. Well, in other words, when you put these things together, AgCl is going to form a solid and sink down to the bottom. But we do know that potassium nitrate still form ions because nitrates are soluble. So now to make our net ionic equation, we need to go through and we need to determine which of these are the same on both sides. K plus is the same on both sides, NO3 minus is the same on both sides, and so our net ionic equation would be Ag plus Cl minus gives you AgCl. Now you're probably asking yourself, does it matter if we put Cl minus plus Ag plus gives you AgCl? No, it doesn't. Convention just says that you usually list the positively charged ion first and then the negatively charged ion afterwards. All right, another example. I already went through and highlighted the compounds in here, but to read it out loud, it says aqueous potassium hydroxide is mixed with aqueous iron 3 nitrate to form a precipitate of iron 3 hydroxide and aqueous potassium nitrate. Write the formula equation, complete ionic equation, net ionic equation. So formula equation. We have potassium hydroxide, KOH. It reacts with aqueous iron 3 nitrate, FeNO3. It forms iron 3 hydroxide, FeOH3, and aqueous potassium nitrate, KNO3. So then we go through and now we reference our solubility rules. So for the complete ionic equation, KOH forms ions because while hydroxides tend to not be soluble, potassium hydroxide and sodium hydroxide are. And as we've said several times already, all nitrates are soluble. And you'll find that nitrates are very common in precipitation reactions because it's a way to get an ion into solution that we know is absolute, and we're absolutely positive are solids. Now, if you don't have your solubility rules handy, you will notice that we have a precipitate of iron 3 hydroxide, but you can also reference your solubility rules that say that all hydroxides are insoluble except for KOH and NaOH. And then, of course, as always, potassium nitrate, which is a very common product, ends up being soluble as well. Now, for that net ionic equation, now we want to see which of the reactants end up on the product side. K plus and K plus are both there. Oh, my apologies. Oh, I did not balance this back here. I apologize for that. This should be a 3 here and a 3 here, which means we should have 3s carrying throughout. So 3 of those, 3 of these, 3 of these, 3 of these. All right. So 3 NO3s are going to be gone. And then our net ionic equation ends up being Fe plus 3 OH minuses give us FeOH3. If you're not sure why I had to go back to add those 3's in there, reference your formula equation. My formula equation, I made the error of not making sure that it was balanced to begin with. We need 3 NO3's on both sides, and because of that I had to put a 3 in front of potassium nitrate on the right side, this guy over here, and since I did that, I also had to put a 3 in front of the KOH on this side. That gave us our 3 OH's, our 3 K's on both sides, and then everything's balanced. We then have to carry that through. And to carry that through means that we would have 3 K plus ions plus 3 OH minus ions. And then we would have 3K plus and 3NO3 minus ions on the other side. And then as you see, it balances out in the end. So this shows you on a reaction scale, on a molecular or atomic scale, what is actually happening during a chemical reaction. We don't just simply put things together and have them react. In fact, if you put the right things together, you're going to end up with no reaction whatsoever. And so it gets a little tricky. You need to know your solubility rules. You need to know what's going to form a precipitate and what isn't. But you also need to recognize that sometimes those net ionic equations show no reaction. In other words, all the ions just stay ions. For example, what if we put KCl and FeNO3 in there? If we put KCl and FeNO3 in there, we would end up with 4 ions that never interact to form a precipitate, and no reaction would appear to occur. So keep those things in mind as you work through the practice problems. There is a formative assessment for this one, so see me when you're ready for that. There's a couple of practices to do along the way, and good luck with your ionic equations.